Laptops, mobile phones, and electric vehicles, they all use lithium-ion batteries to get their energy, and we all want more energy from these batteries. It's really annoying to have to charge your phone every single day, and also we want to drive further when we eventually use these electric vehicles in the future. But it's not just handy gadgets that lithium-ion batteries can be used for. At the moment, renewable energy sources don't really work. They give us energy when we don't need it. And so we need a place to store this energy so that we can use it when we do. So how do we get more energy out of our batteries? Well, first of all, we need to know how it works. So when we plug in a lithium-ion battery to an appliance, the lithium atoms in the anode split into a lithium ion and an electron. The lithium ion moves through the battery towards the cathode, and the electron moves around a circuit, creating a current, and then they reform back in the cathode. Then when we charge our lithium-ion battery, the opposite happens, and they reform back in the anode. The amount of capacity that we can get from the battery is how much lithium we can get into the anode when we charge it. And different materials have different capacity for lithium. Silicon, which is what I work with, has one of the highest capacities for lithium that we know of. However, when we charge a silicon anode, it expands to around 4 times its original size. This causes high stresses in the anode, which can lead to cracking, which can lead to kind of connection loss inside the anode, which can then lead to capacity fade over time. Scientists get around this by creating anodes which have some microstructure to it, so microparticles or nanowires, which reduce the stress, and also try and constrain the silicon by wrapping it in another material. In my DPhil, I mathematically model this expansion of silicon when it's used with a different material, in the hope of trying to find a design which utilizes the high capacity of silicon, but doesn't allow it to expand as much as it does. I apply my model to a microparticle of silicon, which is wrapped in graphite, and then I try and change the size and the shape of the silicon core. I try and incorporate void spaces and porosity into the materials in the hope of finding that best design. However, industrialists aren't really worried about a single microparticle. They want to know what happens to the full anode when we change something about one of these microparticles that makes up the anode. And we can use a technique called homogenization, which allows us to model the full anode as if it was one homogenized material instead of lots of little microparticles with different materials. And this allows us to perform computations of our model a lot faster. Now, if we were to find this brilliant design which uses high capacity but doesn't expand so much that it breaks everything, that would completely revolutionize the transport industry, the energy industry, and make a cleaner future for everyone. Thank you.